Welcome back to the classroom. My name is Mr. Wong. We're continuing on our Year 10 search of Earth and space. Today we're going to be talking about the Big Bang, the origin of the universe. Okay, so the lesson intention today will be to explore scientific observations that are used to explain the origins of the universe. Take note, this is just one of the theories, and this is probably the most accepted theory at this point in time. Your success criteria is to explain why scientists believe the universe is expanding and identify one theory of the universe or the story of the universe. Let's begin. Okay, so to begin ourselves off, let's talk about the Milky Way. The Milky Way is the galaxy that we reside in. If you are in a really remote area on Earth and there's not a lot of light pollution, you should be able to see the Milky Way exterior. So this is what you see here. Now, for a long period of time, people actually believed that the Milky Way was the embodiment of the universe. And they believed that all these little really bright clouds were, clouds, really. We do know that there are many different interpretations over the years. You could look at a previous video where we talked about the historical interpretation of astronomy. But let's look at all these little pieces that brought us to what we now know as the Big Bang Theory. So a really sort of not accurate way of depicting it, but the Big Bang Theory is what we believe is an expansion event that is still ongoing as of right now in our universe. So the idea is at some point in time, about 13.7 billion years ago, the universe that we know of was a very small volume of space, and for whatever reason it began to expand incredibly fast, and then it just continues on its expansion to this day. We don't know why this expansion occurred. We don't actually know what happened right at that specific point either that caused the expansion. We just believe from the data that we have, there must have been a point where the space that this universe was confined in, the universe that we know of, is confined in a very small volume. Well, so the idea that galaxies or there were multiple galaxies came from a couple known as William Herschel and Caroline. Don't know how to pronounce the surname, so we'll leave it at that. So William and Caroline found that the clouds that people were interpreting of the universe were actually stars. And that was sort of the beginning of our changing interpretation of the universe. One of the greatest minds, Albert Einstein, he actually thought the universe was stagnant. Now, there are many theories to demonstrate the idea of a stagnant progression of the universe. Not so much the motion of the universe, though. In the year 1912, an astronomer known as Henrietta did some really important discoveries or observations, so to speak, about particular stars in our universe. We now call them the Serpent variable stars. Essentially, what she was investigating was, in particular scenarios throughout the year, the stars would have different types of brightness, as in the same star, as you can see here, would become brighter or it would become dimmer. And this was a really interesting observation for Henrietta, and it became a really important observation in general for our own understanding of the universe. So what she saw was that stars would vary in brightness over time. She studied two galaxy locations called the Large and Small Magellanic Clouds, sorry for pronunciation, And her observations was that the apparent brightness of the stars would vary periodically, essentially meaning there's a period of time when it's bright, and there's a period of time when it's dim. And these are some really important consequences or significance in her observation, because what she found was stars of similar brightness would vary in brightness within the same period of time. Meaning by, if a star is really far away and another star was really far away, essentially the brightness and dimness period, or the shift of that period, is about the same time. So the longer that shift takes, the closer the star is, or the longer it takes, the further away it is, and brighter it is, and then the closer it is, and the less bright it is. So these stars would also be similar distances away from the Earth. So if we can work out if they have the same shift in brightness to dimness, it's an indication that they're also equally distant from each other, or from the Earth at least. But at that time, we didn't really have a specific way of determining the distance between the stars based on brightness alone. The next observation was also quite important, and this comes down to the concept of the universe expanding. Now, before we get into that, I want to quickly talk about a thing called the Doppler effect. Now, the Doppler effect is caused by the characteristics of light or sound, which act like waves. And the idea is very simple. Say, for example, you have an emergency siren, emergency truck moving towards you. As it gets really close towards you, the pitch of that sound gets higher. And the reason why that's the case is as the fire truck is coming towards you, it generates a wave, or generates a sound to be more exact. So the sound is like this. Now, sound travels at a constant speed in the air. Okay? So equally distanced from each other, you could so to say, from the sound source. However, you can change this if the source of the sound was moving in a particular direction. So say, for example, our fire truck is moving in this direction. Well, if it's moving in that direction, then you get something closer to what you see here. As the fire truck makes one sound wave, it's moving closer towards the right. So when it makes the next sound wave, it's also closer to the right-hand side here, and again, so on and so on. What we will also see is as the fire truck moves further away from its original point where it generated the sound, the waves also get longer and longer apart behind it. So what we can actually dictate is when objects move towards us, we see a smaller wavelength. If it's talking about sound, this could be the case of a higher pitch. If the fire truck is moving away from us, that is going to generate a longer wavelength. And we actually register that as a lower pitch sound, or a lower frequency. So how does that work if it's visible light? Well, visible light, you will know that there's the spectrum, or the rainbow spectrum, from blue to red. You can sort of see this here. Imagine you have a light source and you move it move it away from an observer. As the object gets further and further away, the color turns from blue to red. If it's moving towards you, it goes from red to blue. Okay, what we call this is a redshift and a blue shift. The idea of a light source changing its color appearance to the observer based on how fast it's moving towards you. Okay, if it's moving towards you, it's firstly going to be blue, but if it's moving really fast towards you, it's going to be very, very blue, so to speak. If it's moving away from you, it's going to be red, and so on and so on from there. That's kind of the idea of the Doppler effect. Now, the person who actually looked into the Doppler effect, and now what we call redshifts, is a guy named Vesto. And he explored different types of nebula clusters, galaxies, and he looked at the type of colors that were generated from the different spectras. We'll talk about what spectras are in a second. And what he essentially found was a lot of the stars or galaxies he was looking at appeared to be redshifted. Remember, if you see a red shift or a red transition in space, it indicates that these galaxies and stars are moving away from us. So that's the importance of his findings here with the redshift. Okay, so by analyzing the light from different nebula, dust clouds, he found that nearly all of those observations he was looking at appeared to be moving away from the Earth because it's redshifted. So remember, redshifts indicate that something is moving away from us, assuming obviously it's generating light for us to see. Obviously, again, there's no way we can measure those distances, but at the very least we can see that these galaxies and stars appear to be moving away from us. We can see this using a thing called emission or absorption spectra. So what is emission, what is absorption spectra? Now this is an example of an emission spectra. All elements of the periodic table, when you excite the electrons inside these kind of elements, so say maybe use fire, you might remember from the flame test, different chemicals will generate different colors. If you actually look at the specific wavelength of colors these elements generate, this is what you will see. This is the emission spectra. Okay, that's what we see here. The reason why we see this is because of the way electrons behave inside the atom. So what we actually know is each level the electrons belong to has a specific energy that you preside over. So that's kind of the idea here. I might skip to this diagram to give you a better depiction of what that actually means. Let's look at hydrogen here. Let's say in order for the electron to move down from this step to this step, what the science actually tells us is it needs to release energy. So it needs to release energy. This energy is usually, for the ones that we can see, a type of electromagnetic radiation. And when we talk about emission spectra, we're talking about visible light. Okay? So that's actually how we can actually use the science to look at, what properties are in stars, but we can also look at whether the stars are moving away from us. Another version of spectra is known as absorption spectra. In the case of absorption spectra, that's when an electron needs to migrate up an electron level, and in order to do that, it needs to absorb some type of energy or electromagnetic radiation. Let me show you the difference. Okay? So, emission spectras look like these little bright lines in a dark background. It's an indication, you can see the word photons, but it's an indication of how light is released as electrons are transitioning down the energy levels inside an atom. While as an absorption spectra is an indication, as you can see from these black lines, electrons migrating up those energy levels. Essentially, emission spectra and absorption spectra give you the same information, they just present it in a different way. One is showing the light that's been released, one is showing the light that's been absorbed. And that's kind of the idea there. So what's the significance of that? Well, Hubble basically demonstrated using emission and absorption spectra, again, that we have here, the concept that, he saw a lot of redshifting. So imagine the sun, or being a type of star, it gives you this kind of emission or absorption spectra. So these are like the color patterns that you would expect. These are the type of wavelengths of light that will be absorbed from our sun. Now compare this to the exact same type of star, but one that is moving at 7% of light speed away from us. Can you see how this line and this line here, and these lines subsequently, are more sort of shifted towards the red? Again, remember the key word I said here, it's moving away from us. So this is what we can see if a galaxy is moving away from us. What we expect to be where the line should be, they're kind of more shifted, favoring the left, or not the left, but the red component. So that's what Edward Hubble found. And so he came up with a measurement. So by comparing the wavelengths of the spectral lines of hydrogen for different stars and nebulas, he found that the speed of these distant stars are also quite interesting. He found that the redshift of galaxies were directly proportional to the distance the galaxies had from Earth. So he came up with this idea here. He came up with the idea that as the universe is expanding, the galaxies are moving along this expanded space with it. And so it's generating, as you can see, it's moving further and further apart. So he came up with a nice little graph to show that the universe is expanding continuously away from each other. So he thought the reverse. Perhaps there was a point where the whole universe wasn't expanding, but it was very, very much compressed into one tiny bit of space. This is the actual graph he used to present the data. So you can see on the y-axis is velocity, and down here we have distance. Now there's quite a lot of information here to take into account, but what you need to just sort of appreciate is the further away a galaxy or star is from us, the faster it appears to be moving away from us. Okay? And so that's all the different data sets that you put into place. And that kind of gives you this idea of how far the universe is spread away from each other. But what we can actually show from this pattern, we get a nice little trend line. Okay? As we go down, 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 close to where the stars aren't moving that fast away, or the distances aren't that far apart, we get to a point known as the singularity. It's the idea that at one point in time, the universe actually began as a very tiny volume of space, and we need to use that wording very carefully. It's not a point, it's a volume of space, and for whatever reason, it began to expand like so. And that's what we quote as the Big Bang Theory. Now there's quite a lot of copycats on what this looks like. You have the boy band, that's not correct. You have the reality TV show, or not reality TV, but sitcom, that's not correct either. This is what we mean by the Big Bang Theory. The idea that at some point in time, space-time began, the universe was expanding, and it continues to expand to this day. What we know is our prediction, the universe is about 13.8 billion years old. Okay? Our solar system, our star, our sun began about 4.75 billion years ago. So we're very new in the cycle of this universe here. So that gives us a nice concluding point about the Big Bang Theory. Obviously, there's quite a lot of things to unpack from this lesson. There's quite a lot of new information. But what you need to understand more so is the method in which scientists came together and developed on the concept of the origin of the universe. And that's sort of the beauty about the Big Bang Theory. Alright, thank you for joining. I'll see you next time.